Thank you for the introduction. So, yeah, my name is Touzard, and I'm very grateful that this opportunity has been created to share with you guys the research we do. So, for context, I arrived not in Singapore, but as a prof at NUS in January 2 years ago. And the first people in the lab joined around a bit more than 1.5 years ago. So I'm going to show you the progress that we've made starting from an empty room, populating it, and now doing some exciting stuff. So maybe first thing is that I'm going to give you a bit of motivation behind the work that we do. So what we're trying to do is to harness long-range entanglement between stationary qubits and a traveling photon. So if one can do this, you can form what is called a quantum network. So a quantum network is formed by linking multiple quantum processors by a quantum link. So if you have, if you imagine that you have one of these nodes here in green, the idea is that if you have, if you're in control of one of these nodes in green here over Singapore, you can consider that if it's your node that is trusted, okay, it's a quantum computer that you trust, and it shares a link, a quantum link with other quantum computers that might be in countries or owned by someone else. And so by definition, you don't trust them. They can be in China, in Europe, or the US or whatever. And so what can you do with this kind of infrastructure? You can form a modular fault-tolerant quantum computer where if part of your nodes fail, then you can still retrieve the information encoded redundantly in other nodes. You can also use something called blind quantum computing, where if you control a small quantum computer here, for example, and then you want to use a bigger mainframe from IBM or IQM or whatever, or something else, you can transmit an order to do some kind of calculation and check that the quantum computer, the mainframe that you're using, does not learn about your computation, does not change its results. It transmits you a result faithfully, and it does not know what was the calculation that was done. You can also do device-independent QKD, where you share a classical key, a cryptographic key, but you can check, even if you don't trust the other node, you can check that the transmission of the key has been done faithfully. And finally, a bit of more niche application is quantum sensing, where by using the Heisenberg scaling, if you can entangle several of these quantum processors, and that this quantum processor acts as a sensor, then you can essentially have better scaling of the noise of this sensor, instead of just averaging the nodes independently. So there are, of course, a lot of work to try to do this, and I'll try to show a contrast between what we're doing and what is being done in other groups. So one approach is to just use atomic physics, for example, cold atoms, ions, and to use this as a way to transmit the information. So if you have an atom that you're cooling down, this atom is given by nature, and so it has the transmission, the transition frequency that you will be using will have a certain frequency, and this frequency is not necessarily the one that agrees the best with what is used in telecom network. In particular, telecom networks, they use 1550 nanometer or 1300 nanometer for the lowest attenuation in typical silica fibers. So if you want to communicate the information of 1 qubit here, you entangle it with a traveling photon of the same light, and then you would have to do some frequency conversion here. You can also use microwave solid-state qubits, for example, superconducting qubits or spin qubits, and do the same thing. And in that case, you need to do a conversion that will take many orders of magnitude in terms of scaling of the energy of this photon into the traveling mode. So one of the prime of this approach is that usually it's done with single emitters, and so it has a pretty slow clock speed. And on top of that, this clock speed will decrease with length quite badly, okay? Because of this necessity to have the conversion. So if the conversion efficiency is not so great, then you lose here. And another problem that I think is critical is that if you use this approach, you do conversion, and conversion will map any quantum states onto any quantum state. And this might be a bit too general purpose compared to what you want to do. A quantum network does not need full conversion. So one alternative is that at each node, you can create a pair of entangled photons or a qubit entangled with a photon. You keep part of it onto your local qubit, and you share, you do the same in the second node. And yes, you use an intermediate to swap the entanglement between the photons that are emitted in the middle with the entanglement of local qubit 1 and local qubit 2. What you can prove is that this approach is actually, first of all, is very robust to losses, okay? And the second thing is that once the teleportation is done, it's actually equivalent to a full transduction through teleportation of a state to another one. So this kind of entangled pair source is what is missing in order to do to build robust quantum networks. So in our approach, what we want to do is create at the bottom of one of these dilution refrigerator these devices here that would be sharing 1 microwave photons with QPU and 1 telecom photons that would go in a fiber that you can then launch into an existing network. So we're also not the only ones working on this entanglement-based approach. Some of the remarkable works we recently use electro-optic, for example, where you can use one of these whispering gallery mode resonators in some medium like lithium nanobase, for example, and directly use the modulation of the electric field to convert the electro-optic to create pairs of entangled state, like a two-mode squeezing between electro-optic, microwave, and optic. Another approach to even have a stronger coupling is to use an intermediate mode that is a piezoelectric mode. So the piezo can couple to an optical mode by varying the length of a cavity, literally, and to a microwave mode by just using the piezoelectric effect. So our approach is a bit different. We also use an intermediate, but the intermediate consists in doping a crystal with erbium ions. So what I'll be doing is that I'll discuss what are erbium ions in a bit more details and why they are very well suited for intermediates. Okay. So what is the physics of erbium ions doped into a crystal? So we can do some analogy that would maybe help to grasp the orders of magnitude in terms of other technologies. If you look at this, you don't have a pristine system like an isolated floating atom. Okay, it's inside of a crystal. So what you can prove is that not what you can prove. What you can measure is that if you look at the transmission of this ensemble in the optics, what will happen is that you will not see only one very sharp transition. You will have an inhomogeneously broadened ensemble. And this inhomogeneously broadening is caused by the fact that each atom has a slightly different environment inside of the crystal. So this broadening here looks like as if you were measuring the transmission inside of a hot vapor of gas at room temperature. So the broadening is roughly 1 gigahertz at optical, which is roughly what you find in rubidium, for example. And it can be down to 10 megahertz at microwave. This is done at cryogenic, by the way. It still needs to be cooled down. It's cold, but the inhomogeneous broadening looks like room temperature atomic gas. Now, what is good is that you can, it actually looks as if it was under pressure. It's not at 1 atmosphere, it's above that. You can densify your crystal by doping it at about 50 ppm. And so you can have much higher than, not much higher, but higher density than a gas. And finally, where they shine, sorry for this, I don't know how to get rid of it, is in their, okay, so there's a typo here, in their homogeneous broadening. So if you look at a small part of the spectrum in the middle here, what you will see is that within this spectrum, you will actually stay coherent, okay? If you excite atoms that are within this spectrum, their frequency does not change in time. They stay roughly here. So how much do they not change? Down to 100 kilohertz at optical frequencies, they stay within 100 kilohertz. And so that's the state of the art. And then down to 10 hertz at microwave frequency. So it's actually extremely precise, okay? Very high coherence. So this is more about doped crystals in general, but why erbium in particular? So erbium is rare earth elements. So if you look at the periodic table and you take only the rare earth elements, what you will see is that they have a bit of a particular structure, which is that they carry a pseudospin inside of them. So their pseudospin is actually tighter in the atom than the lower energy shell that is formed outside. And this lower energy shell is what forms the ligand with the rest of the crystal. And so what that means is that when you implant or dope a crystal with this species, the properties of this pseudospin are actually not modified. They don't really interact with the crystal. So the advantage that you have is that if you take erbium, for example, no matter what crystal you put it in, you will always see a peak that is an emission, that is an absorption that is roughly around 1550 nanometer, which happens to be one of the minimum transmission laws for telecom fibers. Now, if you look at something called Cramer's theorem, you will see that even if, so erbium has a very large manifold of spin states in its ground state, and the degeneracy of the ground state has to be even, given by this Cramer's rule. This is a Cramer's ion. So it's not really ideal. What you want is a two-level system instead. But what happens is that once you put it in a solid, the environment in the solid actually splits this degenerate manifold into pairwise states. Why pairwise? That's the minimum that you can get. You cannot go under pairwise as long as you don't have a magnetic field. That's Cramer's theorem. So this pseudospin here, actually what it has is that it has a much larger G factor than just the 2 factor of an electron, for example. So the advantages of this platform is that you don't need any laser cooling, okay? You just put the sample into your fridge and then it cools down, okay? You don't need really high vacuum. It will not get knocked over. As soon as you cool down, the photons cool down and that's it. And the other thing is that this is very well suited for device integration. You can build a ton of things around it, whether it's photonics or microwave circuits, for example. Okay, so now for the application that we have in mind, what are the kind of physical mechanisms that we're going to use? What we're going to use is the fact that if you take a small, what we call a spectral hole into this spectrum of width delta, then for a time scale 1/delta, you're essentially manipulating an ensemble of undistinguishable spins. So if you have 1 qubit on this block sphere, usually you use the representation of its state with the block vector. And if you have n, you have this microspin where now you have some uncertainty on the spin coherent state here, coherent spin state. Okay, so now if you put this atom inside of a cavity, if you're in the regime where they are very well coupled to this cavity, what you will observe is that they will actually synchronize together. That means that if each one of these small spectrum here is a clock, if you want, then this oscillator, this clock, will synchronize with its neighbor. And so this way, what happens is that the emission of the atoms in there, instead of being all emitting at a different frequency, they start to all emit at a similar frequency, and the spectrum of this ensemble narrows dramatically, thanks to an effect that is sometimes called superradiance. Now, the word superradiance is very loaded, so here I use synchronization instead. And now you're kind of back to the physics of a cold and dense gas, okay? All right, so how do we use this for microwave to telecom entanglements? So that's roughly the energy scale, the energy levels of our system, where you have this manifold here of spin 15.5. As I told you, it's actually not, it's not split into 15 states, it's actually split into 2 states with a very large G factor of about 8. And if you put a magnetic field, you observe this Zeeman splitting that can be easily in the microwave regime. Now, naturally, this transition here goes to an excited state, and here it's a broken scale because this excited state is the one at 1550. It's coupled to the optics. Okay, so such an ensemble can absorb and re-emit microwave and optics. If you combine a microwave pulse together with an optics pulse that is tuned to go from this level here to this level here, it can absorb the sum of the two and go here. And now it can re-emit. And if you have a cavity that is tuned here, it will re-emit into a higher frequency. Okay. Now, if you start in the ground state here and you remove the microwave pulse, you cannot obtain this because the Zeeman splitting prevents you from being on resonance. So the way we want to use this is we want to use the power of a transmon qubit, which shifts the frequency of ensembles, okay, in order to use it as a switch for the microwave or optical emission. So what we will do is that we use one of these transmon qubit here. We have these energy levels, and on the couple to these atoms, we have a microwave resonator with a transition frequency that depends on the state of this qubit. When the qubit is in 0, it's on resonance, and when the qubit is in 1, it's off resonance. So if we take the case of qubit in 0, you have an open. In this case, the switch is open. If you send the first pulse in the microwave, it's absorbed, and then it excites the microwave resonator, and finally you get the emission of a microwave pulse. So you go back in the ground state by doing this. And then if you have a second pulse that is in tune with this transition, it cannot reach the excited state. And so you have an emission only at microwave. Now, if you close the switch, if you're in the 1 state, that's the resonance frequency. You excite your ensemble into this microwave transition. It does not go into the resonator. It does not emit a microwave pulse. And then you can reach this excited state. And then you have this superradiant emission. Okay. So that's how we plan to use transmons in order to switch on and off the emission at microwave or in optics. This vision is very simplified, and we obviously have a lot of technical problems, but that's the idea. Okay, so this work is split into, our lab is essentially split into 2 subgroups. One of them is focusing on the emission at microwave condition by a transmon, and the other one is focused on trying to have this enhancement of the emission in the optics. Why this? Well, first of all, if you try to combine in one experiment right away superconductivity and optics, you have problems because superconductors are destroyed by optical transitions. So first, you start by something much simpler, and hopefully you achieve impact with that. So how do you create impact with that? The emission at microwave, the strong coupling between an ensemble and a microwave resonator is something that is already established. It's new science, but it's done. So doing the conditional emission is something that is new. So that's what we're going to try to do. And in a second part, we'll develop the strong coupling with optical resonators, which is something that hasn't really been done before. So in our first aim, strongly coupling the erbium ions with a microwave resonator and gating its emission with a qubit, we use a device that looks roughly like this. On the left here, we have a transmon qubit. On the right, we have this kind of resonator that I will explicit in a few slides. And their substrate, what our substrate of choice is called calcium tungstate. So let's justify a bit our choice of material. So why do we use erbium-doped calcium tungstate? So there is quite a bit of research that is into calculating what is the perfect host for spins. So what you need essentially is something that can easily substitute your erbium with, although to be honest, it's not a strong requirement. If you send erbium with enough energy, it will go somewhere. But the other thing is that you need very low density of the natural abundance of nuclear spins, because nuclear spins will, in the neighborhood of your atom, will cause a dephasing of your atom. That's something we will see later in data. So we have multiple samples, some doped, some undoped, and actually even undoped, you have enough sensitivity to measure the trace amount of erbium in there. Then our resonator here is made of niobium. So why niobium? Niobium is a superconductor. Essentially, its critical temperature is 10 Kelvin, so we work much under that. And its other properties that it has a very high resilience to magnetic field, And in order to induce the Zeeman splitting, that's going to be maybe important, okay? And another thing is that contrary to a lot of higher TC superconductors, it doesn't have a lot of kinetic inductance, and this is important for the design that you'll see. Now, unfortunately, if you want to make superconducting qubits, you always need to have aluminum, because the transmon qubit, the junction, I would say the only really real junction that has been proved to work with high coherence times is made of a sandwich aluminum oxide, aluminum. And that's the state of the art. And it's taking a lot of time to move away from that, even if it's been 20 years plus that it's been used. And finally, if you want to have really high Q superconductors, you use sapphire as a substrate. And so something we will be exploring is to actually build this on sapphire and to put the erbium bonded on top. But that's for another time. Okay, so the first thing is, let's talk about this transmon qubit here. I'm not going to discuss about it in details in the sense that it's a qubit, okay? I'm not going to tell you how it works, just it's a two-level system. If you want to know more, the group of Iban Gao, can, that's their core business. So I'm also not going to talk about how it's fabbed. And here, when I do this, Sakshi in my team, who is just here, and Pavel, I'm just saying I'm not going to discuss 6 months of their work. So it's sad, but okay, that's fine. It took a lot of time to make in-house junctions. So, but what I'm going to show you is that we've essentially managed to have in-house fabrication of kind of state-of-the-art transmons. We make one of these transmons and we house it into one of these microwave cavities here. That's roughly the dimension of the cavity. It's made of copper for good thermal conductivity. And then you house it at the bottom of a dilution refrigerator at 20 millikelvin on the chip. So the contrast is really not very high because it's difficult to take a good SEM of this material. But you have aluminum pads here and a junction in the middle. And here it's a close-up of the junction where you have one aluminum contact that goes to the bottom layer. Then you have a pad here that sticks out that is also aluminum. There is oxide in between and another contact that is contacted to the top electrode here. And so you have this very precise junction here. So I'm not going to tell you why it's a two-level system, but it behaves like a two-level system with what kind of timescales. So if you look at the energy relaxation time, where you take the ground state of this transmon, you put it in this excited state, and you look how long it stays in there. Well, it relaxes with a timescale of 40 microseconds, which is roughly close to state of the art, let's say, like the most common at least. And it's way above what we need anyway. Now, if you look at the Ramsey fringes, by doing at a pi/2, you wait, then you measure sigma x, sigma y by doing another pi/2. And then this measurement here in superconducting circuits can only measure sigma z. So that's why you need to do this rotation here. Then what you obtain with some detuning is these Ramsey fringes with a characteristic time of 20 microseconds, which again is way sufficient for what we need to do. And if you add an echo in the middle, what happens is that you get rid of low frequency noise, and you get this, you also get rid of the detuning, and you get this exponential decay with a timescale of 32 microseconds. So for our entanglement scheme, you need to have done your entanglement within these timescales in order for the fidelity of your entangled state to be good enough, essentially. So our protocol is designed around that. I'm not going to go into too much details. There are a lot of things to present, but that's the idea. Okay, now let's talk about this resonator here. I call it an antenna resonator because you have a very small, actually you don't have an electric dipole for this transition. You only have a magnetic dipole, the spin, and you couple it to this resonator. Essentially it gives it its dipole, like an antenna, its electric dipole, and then you can talk to it. So it has a peculiar shape, okay? It's very lumped element. It has this giant capacitor with a thin microwire. If you zoom next to the wire, the idea is that the spins that are under the wire couple to this resonator through the current that goes to the wire with the magnetic field, the AC magnetic field that goes around the wire that is induced, okay? So why is it designed in this way? is a bit counterintuitive, I think, to most people, at least to me, when I wanted to venture into this field. If you take the Hamiltonian of this LC resonator, you can put it in a very dimensionless form. That is this, where phi is the integral of the voltage, and Q is the number of Cooper pairs on each side of the wire, dimensionless. So it's actually the time integral of the current. Then you have this factor in front, that is RQ, given by this quantum of resistance, roughly 1 kilo ohm. And you have Z0, which is the characteristic impedance of your resonator, square root of L over C. Now, if you look at the quantum value of this phi here, integral of voltage over time, what you get is that these 0-point fluctuations are proportional to Z0 over RQ, square root of that. If you look at the current that goes through this, the phase current relation is given by this 1 over L times phi. So for one photon inside of the resonator, you get a current that is roughly proportional to omega 0. This is fixed, the Zeeman splitting of your ions, divided by Z0, the impedance of your resonator. So you need as low an impedance as possible. So that's why you have giant capacitor, and you use a very low impedance material in order for the current that goes through to create a large magnetic field. And so the value is hidden here, but from our simulations, we find an impedance of 26 ohm, which fits also the data. So how do we fabricate this? I skipped over the fabrication of the transmon, but our lab does a lot of fabrication. So it's a good idea to talk about how it's done. So right now we fabricated on, well, actually it's not fabricated on sapphire. It's fabricated on calcium tungstate, but we also fabricate them on sapphire. So first you deposit some niobium. So this is done with RF sputter. Then you use some photoresist, spin coating, and then photolithography, where you shine some UV light onto this with a mask that gives the shape of this resonator. Then you develop by removing where the resist has either been exposed or not exposed, depending on the type of resist. Then you have a mask here, and you can send with directionality, you can send ions that will eat the metal that is in between, and then you can form these shapes. So then you remove the resist, and you can have very fine features on your resonators. In the actual dimensions of our resonators, so it looks roughly like this. And the critical one is that the wire is 5 microns wide. So this is small, but it's still accessible by just photolithography. So actually the fabrication of this is relatively simple compared to some others. Now it has the wire is in the middle, it's symmetrized, and it has some pads in order to maximize the coupling to the cavity, to maximize the emission of the erbium through this resonator. Okay, so now that we have, so we make this on calcium tungstate directly, doped, and we start putting a magnetic field through our samples. We adjust our magnetic field so that it doesn't destroy the superconductivity, okay? If you know superconductivity, you know that this is, you shouldn't put a high magnetic field next to your superconductors. You create vortices into the superconductor, and then after some critical field, it just disappears, it's a resistor. So because we have a vector magnet, it's actually, you can adjust it little by little until you make sure it's very parallel to this resonator. And once you do this, you have the Zeeman splitting of the ions. And when you have Zeeman splitting, depending on whether your erbium is one isotope with no nuclear spins, or the other minority isotope with a nuclear spin 7.5, you obtain a different splitting. So if you plot the frequency of this splitting as a function of magnetic field, you obtain these. In black, the arrow in black and in green is the resonance frequency of our resonator. And so you will be able to observe this transition once it enters, when its frequency, the frequency of the erbium, is equal to the frequency of the resonator. So and this point is at different values of magnetic field. So we when you do a spectroscopy of this resonator, what you observe is first you observe anti-crossings, so a variation of the frequency of this resonator with the magnetic field, with an anti-crossing type of structure. And beyond just the shift in frequency, you also observe a broadening of the resonance. It becomes much broader. And this is due to the fact that the energy that you send to it, instead of coming back to you, a lot of it goes to the resonator, even if your resonator is not exactly tuned with the spins. And from this figure here, so first of all, you can see that the anti-crossings and enlargements are aligned with these values here that we simulated. And from this, you can deduce multiple things. You can deduce the inhomogeneous broadening of the spins, and you can deduce the ensemble coupling of your spins to your resonator. This ensemble coupling depends on the number of emitters itself. It's not a single spin, it's the total coupling. So the big transition in the middle corresponds to the I equals 0. And this makes sense because most of the isotope of erbium don't have a nuclear spin. And then on the left, it corresponds to the transition between the Mi 7.5 to minus 7.5 to plus 7.5. Now, you can see that for the species with nuclear spins, that the peak of this transition decays here and as a function of magnetic field. And why is that? It's just because for the isotope with spin 7.5, most of the population is in the ground state. And so the transitions from the nuclear spins excited to the higher manifold are suppressed due to Boltzmann population, Maxwell-Boltzmann distribution. So when you have this, it just happens that so first of all, there are other transitions here that we cannot resolve. This can be impurities that are just into the growth of your crystal, and we don't know what it is, to be honest. So we don't care. So now this spectrum here is very characteristic of erbium. How do you know if it's erbium? So how do you know if it's erbium, and how do you know where it is in your crystal? What site is it substituting? Sorry. One thing is that the cooperativity of this 7.5 transition here, as given by the coupling essentially over the kappa internal of the resonator times the inhomogeneous broadening gamma, is over 2. So that means that you're in this strong coupling, collective coupling regime. That is for the 7.5 transition. Actually, it's much bigger if you use this, but actually not what we're using, and I'll justify that in a second. So in order to know what site is being substituted by erbium into your calcium tungstate crystal, usually what you do is an angle-dependent ESR, so electron spin resonance, where you use this resonator, and you look at when the anti-crossing happens. And now this anti-crossing happens at a field that is dependent on the magnetic field, and depending on the angular variation of this, then you can know what symmetry your site has. So then you can make guesses on what species are there and where they are in the crystal. This is a old type of electron speed resonance, but with a new spin, if you want. Okay, so based on this, now we can characterize further our spin ensemble. So the two main characterizations that we can do are same as a qubit, but here, when you do it, its average over all the spins is T1 and T2. Because of the way this system works, it's slightly different. When you do a T1, you actually need to use what is called the inversion recovery sequence, where you do a pi pulse, and then you play this echo type of sequence, where the size of the echo depends on the population that is left after one of these pi pulses. It's a bit complicated, but the curves look the same, so this way you're not lost. So if you do this measurement, what you see is that the amplitude of the echo recovers over a time scale given by 0.57 seconds. That's again for the 7.5 one. So here what we have is an emission that is per cell limited. If you use a cooperativity that is much lower, your emission time is actually over seconds, and actually it's causing a lot of troubles to measure because microwave equipment is usually not made to measure for seconds long. So now for this echo sequence where you do a pi over 2, your spins dephase due to the inhomogeneous broadening, you recover their coherence after a pi pulse and waiting the same amount of time. And when they are back to being all in phase, they will couple strongly to your cavity and emit an echo. If you vary the time between here and the pi pulse, then the echo appears after this delay. And if inhomogeneous broadening is your only decoherence process, it's not a decoherence process because it's actually deterministic. But on top of that, you have this homogeneous broadening, the dephasing of your ensemble. Then the amplitude of the echo will decay over time. And over what time scale? So in this case, the value is not here. It's I think it's 150 microsecond also. So 150 microsecond with these features here. Okay. So the first thing is 150 microsecond. You have superconducting qubits that have higher coherence than that. So it's not very impressive, okay? But it's far from being state of the art. In this material, so this optimized material, the best that has been measured is 20 millisecond. And actually, if you look at what host you can put erbium in, it's very unlikely that we'll go somewhere much above that, maybe 40 millisecond, but at least without refinement of isotopes without nuclear spins. So now, on top of the fact that the T2 is not state of the art, which, sorry, we think that it's just due to the fact that due to the high doping of this material, the different parametric species next to one another, they essentially they cause a problem with one another. So if you have an undoped sample, which is where the best T2 has been measured, most likely we'll measure a similar one. There's no reason, it's the same suppliers. So what causes this envelope modulation here? It's a phenomenon that's, to be honest, I didn't know a month ago. It's called ESIM. So ESIM is electron spin echo envelope modulation. So when you do your echo, you have some, actually you think you're exciting only a two-level system, but because of the different polarizations of the nuclear spins that are close to your erbium, you have various shifts in your transitions depending on the environment. And statistically, depending on the natural abundance of elements, you will not have something that is completely random. You will always have 10% of nuclear spins from tungsten, for example, that are at a certain distance, and then they modulate this envelope here. One important thing to note is that if you use a higher field, you polarize the nuclear spins much more and more. So at high field, all this decoherence disappears and the coherence time actually increases dramatically. And now at higher field, you could say, oh, but if it's higher field, you are not going to be at the right frequency to measure these spins. But if you look at this diagram here, what you see is that if you actually wrongly align your magnetic field parallel to the wire, then the resonance frequency with this resonator is actually obtained for a much larger value of the magnetic field. If you want to have a higher T2, and it's actually you might think that it's a problem for superconductivity, but actually, as long as you have a good vector magnet to align your field with the superconductor, it's actually not a problem. Okay, so now let's conclude on the superconducting qubit part. So what we're going to do is that we're going to use lower cooperativity because our protocol, we found out that it's enough to do what we want to do for the entanglement with the transmon. And also it's easier to simulate because when you have low cooperativity, you can essentially separate the simulation of each spin family, like if you have and the cavity, because if the coupling is small, then the coupling between each frequency class of spin is actually going to be small. So it's also easier to simulate. We'll see if by lowering the concentration, we also improve on T2. We'll test devices built on Sapphire and then with integration on top of the calcium tungstate and see if you can get a higher quality factor for your resonator, which should improve the Purcell factor. And the next thing is that in order to get a strong emission of the erbium through this resonator, what you need is you need to couple your resonator, that is so schematically here, to your cavity. You need to couple it a lot. To do this, usually you put a pin on the side and you put it very well into the cavity to act as an antenna to take all the signals away from this cavity. Now, if you have a transmon and this resonator on the same chip, what people in superconducting circuits know is that this will also destroy your transmon. So a typical trick in order to have strong emission at the frequency of the resonator, no emission at the frequency of the qubit, is that you use what is called a Purcell filter. You just suppress the density of state around the frequency of the qubit, and this way it cannot emit. One way to do this in 3D is that you add a waveguide. For a waveguide, some frequencies go through, some frequencies don't go through. If you tune these waveguides are commercial, they are used for military and aviation stuff. And if you design the size of the waveguide well enough, you can have a cutoff that is somewhere between the cavity and, between the resonator and the qubit. And so I implemented this in my thesis. That's from my thesis. So that's where the idea comes from. Okay. Okay, so now abrupt change of gear. We're going to go on to optics. That's a bit of the difficulty of the lab, if you want, is that first of all, I did very little optics in only as a postdoc, and also both of these fields they have a strong entry cost, and so it's difficult to maintain both of them at the same time. But it's in exchange, it's really fun. You know, I'm really learning a lot, and I love it. Okay, so in the optics side, as I said, one important point about these spins in these atoms inside of a crystal is device integration. It's something that is very difficult to do with floating atoms. So what we're going to do is use these facts for coupling them to optical waves. When you use optical waves, you can confine them into a waveguide on chip, and then the electric field is much more concentrated, and so the coupling becomes much stronger compared to trying to focus a field in space, or also compared to whether when these atoms just emit on their own. So this figure here shows a waveguide that is made of a material called lithium niobate. This lithium niobate is put on top of cladding, so a material that has a lower refractive index to have total internal reflection inside of the material. This layer is 300 nanometer. This layer is 1 to 2 micron. And under you have a handle wafer just to hold this entire thing. You can actually also add electrodes on the side of these waveguides in order to for a property of lithium niobate called electro-optic effect that I'm going to talk about now. So why do we choose this lithium niobate on insulator? Okay, if you've heard about photonics, that's probably maybe not the first material you've heard of. Most you might have heard of silicon nitride, silicon on insulator. But lithium niobate was exotic a few years ago, and now it's very established, thanks in part to the work of people like Trudy there, and Sahao. I saw him somewhere here. Yes, it's here. So in Harvard and Yale, for example. Okay, so one good thing about it is that well, it's been used forever for electro-optic modulators. Okay, it has a strong electro-optic effect. Now it's really readily available in very high quality crystals with very thin layers that are directly bonded onto silica, cladding here, using smart cut techniques. So it's a very, very good technique that allows you to work with a lot of different substrates. The advantage of lithium niobate is that it has a very wide transparency window. If you look at silicon, if you look at a wafer of silicon, it's actually opaque, right? So lithium niobate is actually transparent, so you can put visible light through it. This is useful to pump things like laser pumping or second harmonic generation. Another thing is that, yes, it has a very large electro-optic coefficient. If you put a voltage across a waveguide like this, you can induce a change in optical path in this waveguide that is fairly large without putting a lot of voltage. And in particular, without current going through. So it's a very low power process. So you can actually pull the way the index changes as a function of electric field depends on the domain of the crystal. And what you can actually do is that by inducing electric field that is wide enough, you can actually create new domains inside of this waveguide. And this is used for polling. And this, so it's, you might have heard of periodically poled lithium niobate to create pairs of photons. So that's what it is. But now you can do that in integrated photonics. So this type of device, what we want to do is to integrate our calcium tungstate on top of it. So this kind of heterogeneous integration has been done in the group of Hong Tong, in part by Sir Hao, who is here. So what we want to do is to continue on that work. What they did is that their coupling here was not as strong as they would have liked, and then they moved on to something else. So we're looking at why it's not as the coupling is not as good as what it could be, and try to improve on that. So we're taking over their work. So what we're trying to do is to use thinner lithium niobate to improve, to diminish the volume of the mode, and the Purcell factor depends in 1/, the mode volume. We're trying to improve on the adhesion layer between the two substrates. And while doing that, we also know that the calcium tungstate has a refractive index that is closer to lithium niobate, so that the wave is less confined into the lithium niobate. So because of this, you have a stronger participation of the field inside of the erbium doped substrate. The only thing you need to be careful about is whether this can be bent correctly, the waveguide, so that you can direct the light well. So this is an isometric view. The idea is that the device that we make is a ring resonator, where you have a bus waveguide that inputs some light, and then the wave, part of the wave overlaps with this waveguide that is biting its own tail and travels like this. If after one turn you're in phase with the light that is coming here, what you get is a traveling wave resonance. So the wave is not bouncing off a mirror, it's just turning and turning and turning, but the energy builds inside of it. And the advantage of this structure is that because there is no mirror, it can be extremely high quality factor. We have our chip on top of it. You can tune the resonance with electrodes on the side, and then this substrate actually takes over the entire chip. Okay, so lithium niobate is great. So why doesn't everyone use it? Okay, why? Because first of all, it's not CMOS compatible, so it's very difficult to convince any fab to work with that. They just like, no, it doesn't come into the room even. So what are the challenges besides that are caused by this material? So what we're trying to make is this kind of device. You have the scale here. You have a bus waveguide, you have a ring resonator. The coupling here is done with what is called a pulley coupler. So where you go around the ring, and so that you have a large overlap with, despite the fact of having a relatively wide gap between the waveguide and this. And on the end of this waveguide, you have grating couplers. So it deflects light at a very certain frequency. So 1550, it's tuned for that. To get from a fiber that comes from outside the plane of the chip into the chip. With this, you get approximately a bit less than 10 dB of loss per facet. This is an easy to use alternative to trying to bring a fiber exactly on the side of the chip. What you see here is leftover lithium niobate, and here is protruding lithium niobate as seen from the previous picture. So if you take one of the stack that you get from your supplier, it looks like this. You have silicon, silicon oxide, lithium niobate. And the way you fabricate these waveguides is that you put a thin layer, so a layer of resist on top, the same as the fab that I showed for the metal part. And then you use ions that are going to eat the material directionally to eat the sides and form this waveguide. So now the problem is that if you work with a traditional material, this process is actually very much helped by chemistry. The resist is inert to the gas that you send, while the material is not, and then it just gets eaten, and what is left over goes into the air, and you suck it outside. The problem with lithium niobate is that you cannot do this. If you try to use a chemical etch, then it forms some things that are non-volatile. It stays on the side, and it creates this kind of blobby like edges, very rough edges, and then you have a lot of losses into your waveguide. So what people figured out is, okay, we cannot do chemical etch. The etch is going to be slow and not selective, meaning that you're going to have to etch this layer as much as you're etching this. And you use only a chemical etch. That means that literally you take an ion as inert as possible, so argon, you accelerate it and you break the material as much as you can. And of course, it doesn't matter. I mean, it matters if it's hard or soft. The resist here is softer, so you eat the resist actually sometimes twice as fast as the material if your etch is not very good. Now, because your etch actually destroys the resist, that means that over time, if your lithography is not very precise, you will actually have your mask will change over time, and it will create some micro roughness on the side of the waveguide here. The form will not be regular. It will also create some of these problems. So for this, DuPont developed essentially this HSQ resist that is very dense. It's like glass inside of some polymer. And it's very dense so that even when you spin it, it forms a very high layer of resist. And very high, if you've done fab, you should know that very, very thick resist is usually not compatible with very precise fab. So here, that's where the challenge lies, is that you need to do a very precise 10 nanometer or so E-beam fabrication onto a very thick resist. So it's very unforgiving. So that's why we've worked on developing this for quite some time, and now we roughly got it thanks to Pavel and the rest of the lab, but mostly from Pavel. So once you do this, you end up with an SEM picture of one of these waveguides. So this is like this is a good one. Okay, I didn't show a picture of a bad one. Where this is a waveguide. Here, this is another bigger waveguide next to the pulley coupling here. And what you can see is that the sidewall here is extremely smooth. So this is what we consider state of the art. Essentially, it's it's difficult to get better than this. At least it's good enough for us. Now on the SEM, there are some other parts where you can see some of this micro masking. It's like, so you make one mistake into your pattern, it will get imprinted onto the waveguide very precisely, and then it shows in losses. So even if this is very good, as we'll see with the results in 2 minutes, we actually see some very obvious improvements that should give us even better results. So if we make a resonator with this waveguide here, so this is actually this one, we input some lights and we look at what it comes out the outputs. Where there is a resonance of the ring, part of the light will go into the ring, and so it will not come back out. And in particular, it will, if exactly half of the light that goes into the ring is eaten away by losses, then it will interfere destructively with what is trying to go through. And so you get these very sharp dips at what is called the critical coupling of these ring resonators. And by looking at the transmission by the width of the transmission of these peaks, what you get is the quality. You can fit the quality factor, internal, and coupling. So if you do an inset, a zoom onto this transition, what you see is a very sharp dip that is much less than 1 gigahertz. So this gives you an internal quality factor of 1.5 million. So I know that the state of the art arguably is a bit better than that, but I don't think there are many groups that can do this. So where a few months ago we needed to ask Drudy to essentially make a chip for us because we didn't have this capability. Thanks to some guidance from him and a lot of hard work in the clean room, we managed to have this thing. And so now is the good time to start measuring our devices. One last part that is critical to our work is the wafer bonding. Okay, so wafer bonding is very far from being trivial, especially with the material that we chose. So the idea is that you have this lithium niobate surface on the bottom. You have this calcium tungstate surface. Both of them are very well polished. You buy them like this. They are polished enough that you can grow something epitaxially on it. And when you want to put them in contact with one another, you don't want them to be able to leave anymore. So the way you do this is that you populate with chemistry each surface with a lot of these hydroxyl groups. And when you put them into contact, they will create hydrogen bonds between one another. These hydrogen bonds are quite strong. Once you do that, if you try to remove it or flip it like this, it doesn't fall. But it's reversible. You can remove it and you can put it back. If you warm this up, then what you form is covalent bonds. and but you need relatively high temperature annealing, and this causes problems. So the way we developed our own way of doing this, and of course it's inspired by research, but it's slightly different. What we do is that we take these two pieces. First of all, we clean them with regular solvents. Then we use this piranha cleaning. So piranha cleaning is based on very activated, so sulfuric acid activated with peroxide. So peroxide makes it even worse if you want. Sulfuric acid is very good at carbonizing, so it means that it will eat your hand. So this is dangerous. Then we use this SC1, so standard cleaning one. This cleaning developed by the American Radio Corporation in the 60s. So anyway, it's something that is used everywhere in the semiconducting industry. So here you have hydroxide activated ammonia, and this will create your thing. And also it will remove any particles that is on the surface. It will activate it so that it doesn't want to stay close to a surface. So then it goes into a solution. Then at the end, you obtain a very clean, no residue surface. And if you put a drop on it, it will spread all over. So this means that it's very hydrophilic. And so if it's very hydrophilic, it means that it's a smoking gun of having a lot of these hydroxide bonds. Then when you touch them onto one another, you cannot pull them, at least with tweezers. What you get is this kind of device here. So it's aligned by hand, okay? Like right now, it's a bit artisanal. So if you make so we have two waveguides here that are rotating onto one another. They are here and here. Then we built this kind of mesa here to have the calcium tungstate to fit flush on top of the waveguide, and here it's stuck. Okay, so how stuck it is it? So what Bernard here did. So Bernard is the guy responsible for developing this bonding. What we've tried is that you can use a bond tester that puts a load onto the side and see if it delaminates or not. Right now, we've tested up to 5 kg and it doesn't delaminate, okay? So it's quite strong. Most likely the substrate might break before it delaminates, but we need to try even higher weights, and that should be good. So now the only problem with this is that's a problem that Sir Hao did not get when they tried this in Hong Tong's group, is that because of the fragility of calcium tungstates and because of the difference in coefficient of thermal expansion, when we cool this down, generally we get a crack into this. Now it's not you get a wide area with no crack, so it's okay, like it's mostly okay, but it's not exactly the most deterministic. So there's still a bit of progress to do with this. What we're doing right now is playing with adhesion layer to allow some plasticity in between, like a very small ALD layer in between. And also I want to investigate other materials that would be much harder than the calcium tungstate. Calcium tungstate is just extremely brittle. Oh, there is this. Okay. I'm a bit at the end of my time, but so I'll go through that quite quickly, okay? So the last thing that we have is we're trying to be able to measure signals of light that are sensitive enough to work at a single defect level. So that means that, so let's see what that means, okay? Our choice for this, contrary to most, so yeah, I don't really know why I made this choice. That's because that's what I know from superconducting circuits. I use heterodyne measurements. And I think in the end, it has a lot of benefits compared to the traditional approach, which is to use a single photon detector that can detect most photons. You put a narrow filter in front of it, and then you select only the photons in that. So the idea of the setup that we have is that if you use a laser here, you split the signal between a LO branch and a signal branch at the bottom, and you combine them onto a bin filter. And what you measure here is the symmetric and anti-symmetric superposition of the LO and the signal. If you subtract the signal and look at it on the spectrum analyzer, you see a beat signal between if the LO and the signal are detuned from one another. If you look at the quantum mechanics behind, what you can see is that the difference between the measurement of this and this gives you a term that is proportional to the quadrature of your signal multiplied by the average value, the expectation value of your LO, which is usually in a coherent state. And if you look at the noise on this operator. If you have many more photons into your LO than into your signal, then the noise is proportional to your LO power or LO number of photons. And so if you divide this by the square root of that, what you get is that you can get with very high efficiency the quadrature of your signal. Now, right now, what we're doing is that we only want to measure the amplitude. So we just don't stabilize this amplifier, this interferometer. We just let it run, and we just look at the amplitude on the spectrum analyzer, something that is not phase sensitive. So in theory, what you get is detection in a narrow band without adding a filter that is limited only by quantum mechanics, and so no dark counts, and that you don't need any cryogenic detector. So I think it has a lot of advantages, but it's not very widely used. In practice, your spectrum analyzer, when you turn it on, it already shows some noise. So you choose the bandwidth of your spectrum analyzer, and it gives you some noise. And when you add your detector onto it, it will have some amplifier that is used, and maybe it's hot, etc. So it adds a lot of noise here too. So it's not exactly perfect. But then if you put enough power into your LO, this amount of noise starts to be beaten by the shot noise, so the quantum mechanics noise of the LO. And in that case, the amount of by which you beat the technical noise with the shot noise gives you what is the limit on your quantum efficiency of your detector. So what we do is that if you plot the signal to noise ratio, where this is the signal plus noise and this is the noise only, as a function of number of photons in a 10 kilohertz bandwidth, you get this plot. It's a linear dependence. And what you can deduce from this is that the efficiency, the quantum efficiency of your detection is 73%, which is not state of the art, more in the 90, but it's still, like this, it's still very good. I'll translate that in 1 second in other terms. Now you can use multiple bandwidth. And if you look at the minimal optical power, so not translated into photons, you can measure much under minus 120 dBm. And in theory, if you decrease the bandwidth of your measurements, you can even measure higher than that. But right now we're having a bit of troubles here. It saturates a little bit. So if you translate that in terms of single photons, if you have 1 photon per second, which is extremely low, the power of this would be minus 160 dBm. But nobody measures this. Like even the dark counts of a single photon detector are still much higher than this. So it's comparably hard to detect. Now, if you look at erbium, naturally, it has an emission time that is in the millisecond. So the power the power of the signal generated by erbium would be in the minus 130 dBm. And if you look at most experiments with erbium coupled to a resonator that enhance their emission by a large factor, they end up having a lifetime that is in the 10 to 100 microsecond. So that gives you a much higher enhancement than this. So in these experiments, in theory, we can measure erbium ions at the single emitter level with a high SNR. Okay, so to conclude, we established state-of-the-art fabrication for transmon qubits, spin-sensitive superconducting resonators, lithium niobate ring resonators, and die bonding between photonic and host. We've established measurement capabilities at cryogenic for both superconducting circuits and photonics. And we've established single spin capabilities, not in the microwave, only in the photons. So towards our original high impact goals is to do this transmon condition spin echo, a bit more fab, and then we're there essentially. And super radiance of erbium emitters at telecom wavelengths. We have the most of the device done and a bit of tweaking and then measurement. So I wanted to introduce the team that is behind this work. So they are all here besides Kartik and Kong. And as you can see by how we're dressed, it was taken half an hour ago. So, okay, so on the optical side, we have Kartik, Pavel, and Bernard and Kong, who do most of the work, measurement and fabrication. With Pavel being our postdoc dedicated to fab essentially at this point, who works both on superconducting and optics, but right now mostly optics. On the circuits, so Nirmala is our FYP. I didn't count her in, but she also worked on the optics. On the superconducting circuit side, we have Sakshi that does a lot of fab. Kritika does a lot of measurements. Bruno is here. Bruno is RA. He will be leaving for Keysight soon, and I'm very happy about his next step. And Alexander is joining us for the summer. Impact. Now, I haven't talked about, so that's part of the activity of my lab. I completely didn't talk about another activity, which is to make quantum limited superconducting amplifiers. We didn't have time to talk about that, where we have Sherwan, Chen, and Wei Hong and Li Ye who work on it. That project is QEP sponsored. That should end next year. And we also have a lot of exciting things to discuss about that cannot fit into this talk. So what I would like you to do, if you have questions, obviously you can ask me, but don't hesitate to reach out to them and to discuss their projects. And I'm sure they would be really glad to talk about it. I don't think I forgot anyone, right? All right, cool. Thank you very much for your attention.